Welcome and introduction. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are going to look at one of the most fundamental concepts in Google Cloud Platform, which is the resource hierarchy, and we will also examine how organization policies are applied across that hierarchy to enforce governance and compliance at scale. The resource hierarchy in GCP is the structural backbone of every Google Cloud deployment. Unlike AWS, where accounts are largely flat under an organization, or Azure, where you have management groups and subscriptions, GCP provides a clean four-level tree that gives you precise control over identity, access, billing, and policy from a single root all the way down to individual resources. Let me walk you through this diagram, which shows the four levels of the GCP resource hierarchy. The organization node is the root of the entire tree and represents your company in Google Cloud. The organization node connects to folders, which act as a grouping layer for departments, environments, or business units. Folders then connect to projects, which are the workhorses of GCP where resources actually live. Finally, projects connect to resources such as virtual machines, cloud storage buckets, and BigQuery datasets that perform the actual work of your applications. Throughout this presentation, we will look at each layer in depth, build out a real hierarchy using the gcloud command line, and then attach organization policies that enforce rules like restricting which regions can be used, blocking external IP addresses on virtual machines, and limiting which identity domains can be granted access. By the end, you should have a complete mental model and the actual commands you need to design and govern a Google Cloud landing zone. The organization node. Let us start at the very top of the hierarchy with the organization node. The organization node represents your company in Google Cloud, and it is the root container for all of your Google Cloud resources. The organization node is automatically created when you sign up for Google Workspace or Cloud Identity using your company domain. So if your company owns the domain example.com and you set up Cloud Identity for that domain, Google Cloud will provision an organization node tied to that domain. Every Google Cloud resource that anyone in your company creates can then be associated with this organization node. The organization node has a unique numeric identifier called the organization ID, and that identifier is what you reference when you run gcloud commands or attach policies at the root. It is permanent and cannot be changed. At the organization level, you typically grant a few very privileged roles. The organization administrator role gives a user the ability to define IAM policies and manage the structure of the entire hierarchy. The Organization Policy Administrator role gives a user the ability to set organization policies that govern the entire company. These roles should be assigned to a small group of platform engineers or a break glass account, not to regular developers. Let me walk you through this diagram. The Cloud Identity domain represents your company's identity provider, which is typically your Google Workspace or Cloud Identity tenant tied to a verified DNS domain. The Cloud Identity domain provisions the organization node, which means the existence of the organization node is dependent on having a valid identity tenant. The organization node then anchors three things. It anchors the IAM root, which is the topmost point where identity and access management policies can be defined. It anchors the policy root, which is the topmost point where organization policies can be applied. And it anchors the hierarchy root, which is the parent container for all folders and projects in your Google Cloud estate. Without an organization node, you can still create standalone projects, but you lose all the centralized governance capabilities that make Google Cloud safe to operate at enterprise scale. Projects. Now we arrive at the project level, which is where most of the actual work in Google Cloud happens. A project is a container for resources, and it is also the unit of API usage tracking, quota management, billing attribution, and service enablement. Every Google Cloud resource must live inside a project. You cannot create a virtual machine, a cloud storage bucket, or a BigQuery dataset that floats outside of a project. The project is the atomic unit of resource management. Projects have three identifiers that are important to understand. The project ID is a globally unique string that you assign when you create the project, and it is immutable for the life of the project. The project number is a globally unique numeric identifier that Google assigns automatically, and it is also immutable. The project name is a human-readable display name that you can change at any time. When you run gcloud commands or write Terraform configurations, you will almost always reference projects by their project ID. Each project links to a billing account, which is where all of the charges incurred by resources in that project are tracked. A single billing account can fund many projects, which is the typical pattern in a large enterprise. The project also has its own set of enabled APIs, its own set of YAML bindings, and its own set of organization policies that may further restrict what the inherited policies allow. Let me walk you through this diagram. The project container is the central unit, and it has several attached components. The project ID is the immutable string identifier that you choose at creation time and use in all your tooling. The billing account links to the project and receives all the cost charges for resources inside it. The YAML bindings attach to the project and define which identities have which roles on the project. The enabled APIs list attaches to the project and tracks which Google Cloud services are turned on. From the project, the actual resources branch out, including compute engine virtual machines, cloud storage buckets, BigQuery datasets, and Cloud SQL instances. All of these resources inherit their identity, billing, and policy context from the project that owns them. Creating projects under folders. With our folder structure in place, we can now create projects and attach them to the appropriate folder. Projects are where your actual workloads will live, so the placement of a project in the hierarchy determines which YAML grants and organization policies it inherits. The first command is gcloud projects create. The gcloud projects create command provisions a new project under a specified parent. The first positional argument is the project ID, and we use the value webapp prod 001, which must be globally unique across all of Google Cloud and cannot be changed after creation. The name flag provides a human-readable display name, and we set it to webapp production, which is what appears in the Cloud Console UI. The folder flag specifies the parent folder that the project will live under, and we pass the folder ID of the web tier prod folder that we created earlier. This anchors the new project inside the production web tier branch of our hierarchy. The second command links a billing account to the project, because a fresh project has no billing account associated and most APIs will not function until billing is attached. We use gcloud billing projects link followed by the project ID as a positional argument. The billing account flag specifies the billing account identifier, which is a string in the format 3 groups of 6 hexadecimal characters separated by hyphens. Without this link, attempts to create resources that incur cost will fail. The third command enables the compute engine API on the project. Most Google Cloud services require their corresponding API to be enabled before you can use them. We use gcloud services enable followed by the API service name compute.googleoffice.com, and the project flag specifies which project to enable the API on. After this command succeeds, you can create virtual machines, networks, and disks in this project. Finally, gcloud projects describe with the project ID as a positional argument retrieves the full metadata of the project, including its parent folder, its project number, its lifecycle state, and its create time. This is your verification step to confirm the project landed in the correct location in the hierarchy. Applying organization policies. Let us now look at how to actually apply organization policies using the gcloud command line. We will apply a list constraint that restricts resource locations, and a Boolean constraint that blocks external IP addresses on virtual machines. The first command is gcloud resource manager org policies set policy. The gcloud resource manager org policies set policy command applies a policy definition from a YAML file to a target node in the hierarchy. The positional argument is the path to the YAML file, which we name resource locations, YAML. The folder flag specifies the target node, and we pass the folder ID of the production folder so that the policy applies to everything under production. The YAML file itself contains the constraint name, which is constraints/gcp.resource-locations, and an allowed values list. The allowed values list contains two value group entries, in/locations/is central 1 and in/locations/is east 1. These value group entries are special multi-region identifiers that include the region and the related zones and multi-region storage buckets. After this policy is applied, no one can create a resource outside of those two regions inside the production folder, no matter how much IAM access they have. The second command applies a Boolean constraint. We invoke gcloud resource manager org policies enable enforce with the constraint name as the positional argument. The constraint name is constraints/compute.vm external IP access in the simplified form, but for the Boolean external IP restriction we actually use constraints/compute.vm can IP forward style constraints, and in this example we use constraints/compute.skip default network creation, which is a true Boolean constraint that prevents the default VPC from being auto-created in new projects. The folder flag specifies the production folder so that this enforcement applies to every project that lands in that folder going forward. This is a very common landing zone pattern because the default VPC has overly permissive firewall rules that most enterprises do not want. The third command lists all of the policies currently set on a node. We use gcloud resource manager org policies list with the folder flag pointing at the production folder. This is your audit and inventory command, and it returns every constraint that has been explicitly set on that folder along with whether the constraint is inherited from above. Finally, gcloud resource manager org policies describe takes a constraint name as the positional argument and the project flag pointing at a specific project. This returns the effective policy on that project after taking inheritance and any local overrides into account, and it is the single most useful command for troubleshooting policy behavior. Policy inheritance and effective policy. To close out our look at organization policies, let us examine how inheritance works in practice, because this is where most policy bugs originate. By default, every node in the hierarchy inherits the organization policies from its parent. So if you set a policy at the organization root, every folder, every nested folder, every project, and every resource underneath will be governed by that policy. This is the default, and it is what gives organization policies their power to enforce company-wide rules from a single control point. However, you can override inheritance at a lower node. There are two override mechanisms. The first mechanism is the inherit from parent flag, which is true by default and can be set to false to break the inheritance chain at that node. The second mechanism is the reset flag, which clears any local configuration and restores the inherited value. Understanding these two flags is critical when you are debugging why a policy is or is not in effect on a specific project. The merging behavior also differs by constraint type. For list constraints, the effective policy can be the union or intersection of the inherited and local values, depending on whether you set inherit from parent to true or false. For Boolean constraints, the local enforcement value simply overrides the inherited value when inherit from parent is set to false. Let me walk you through this diagram which shows policy inheritance in action. The organization node has a policy applied that restricts resource locations to US Central 1 and US East 1, which represents the company-wide default rule. The organization node connects downward to the production folder, and the production folder inherits the location restriction without any modification, which is shown by the inheritance arrow labeled inherits. The production folder then connects to the web tier production folder, which adds an additional Boolean policy that blocks external IPs, while still inheriting the location restriction from above. The web tier production folder connects to the web app production project, which inherits both the location restriction and the external IP block, but also adds a project-specific override that further restricts the allowed regions to only as Central 1, removing as East 1 for this particular project. This cascading model means the web app production project ends up with 3 effective rules in force, 2 inherited and 1 local, and the effective policy command is what you would use to confirm that final state. In the next part of this series, we will go deeper into custom organization policies, the new tag-based policy attachments, and how to use Terraform to manage your entire hierarchy and policy set as code. Common Landing Zone Policy Catalog. Now that we understand how organization policies attach to the hierarchy and how inheritance works, let us look at the practical question that every platform engineer faces, which is which policies should you actually turn on in a new Google Cloud landing zone. Google publishes hundreds of predefined constraints, but in practice there is a fairly small set that almost every regulated enterprise deploys on day one. These policies fall into 5 broad categories, and learning the names and behavior of these specific constraints will get you through the vast majority of governance requirements. The first category is network controls, which restrict how virtual machines and networks connect to the public internet and to other VPCs. The most important constraint in this group is the one that blocks external IP addresses on virtual machines, because external IPs are the easiest way for a misconfigured workload to be exposed to the internet. The second category is IAM controls, which restrict who can be granted access and how service accounts can be used. These include the constraint that blocks identities from outside your company domain, the constraint that disables the creation of service account keys, and the constraint that prevents creation of new service accounts beyond what is strictly needed. The third category is storage controls, which prevent cloud storage buckets from being made public or accessed through legacy authentication methods. These constraints address one of the most common cloud security incidents, which is the accidentally public S3 or GCS bucket exposing sensitive data. The fourth category is compute controls beyond just external IPs, including constraints on which compute images can be used, which machine types are allowed, and whether shielded VM features are required for all instances. The fifth category is location controls, which restrict the geographic regions in which resources can be created, often driven by data residency regulations like GDPR or financial industry rules. Let me walk you through this diagram. The landing zone policies node is the central concept, and it branches into the 5 governance categories we just discussed. The network controls branch contains the external IP restriction and the VPC peering restriction. The IAM controls branch contains the domain restriction, the service account key restriction, and the service account creation restriction. The storage controls branch contains the uniform bucket access requirement and the public access prevention. The compute controls branch contains the trusted image requirement and the shielded VM requirement. The location controls branch contains the resource location restriction. Together, these 10 constraints form the baseline that platform teams typically apply at the organization node, so every project inherits them automatically. Service account hardening. The next group of policies we want to enable in any production landing zone are the service account hardening constraints. Service accounts are the identities that workloads use to authenticate to Google Cloud APIs, and they are also one of the most common attack vectors when poorly managed. The first constraint is constraints/IAM.disable service account key creation, which is a Boolean constraint that blocks the creation of service account JSON keys. Service account keys are long-lived static credentials that, if leaked, give an attacker full access to whatever the service account can do. Modern Google Cloud workloads should use workload identity federation, attached service accounts on Compute Engine and GKE, or short-lived OAuth tokens, none of which require exported JSON keys. Turning this constraint on prevents anyone from generating those static keys in the first place. The second constraint is constraints/IAM.disable service account creation, which is another Boolean constraint that prevents new service accounts from being created in a project. This is often too restrictive for application teams, so it is typically applied only to highly sensitive folders or paired with a process where platform teams centrally provision service accounts on behalf of application teams. The third constraint is constraints/IAM.automatic IAM grants for default service accounts. By default, when you enable a Google Cloud service in a project, Google creates a default service account and grants it the editor role on the project, which is an enormous amount of privilege. This Boolean constraint blocks that automatic grant, forcing teams to explicitly assign only the minimum necessary roles to their service accounts and removing one of the most surprising and dangerous defaults in Google Cloud. The code block shows the commands to enable all three of these Boolean constraints at the organization node. The gcloud resource manager org policies enable enforce command takes the constraint name as the positional argument and the organization flag specifies the parent node where the policy is set, which is the organization ID. We invoke this command 3 times, once for each constraint, and after all 3 succeed, every folder, project, and resource under the organization is protected by these 3 rules. To verify, we run gcloud resource manager org policies list with the organization flag pointing at the organization ID, which returns every policy currently set at that level along with whether it is being inherited from a parent. Since the organization is the root, all of these will show as locally set rather than inherited. Identity domain restrictions. One of the most important and least known organization policies is the domain restriction constraint, which controls which identities can be granted any IAM role anywhere in your Google Cloud estate. The constraint is named constraints/IAM.allowed policy member domains, and it is a list constraint that accepts customer IDs as values. A customer ID is a unique identifier for a cloud identity or Google Workspace tenant, and it always starts with the letter C followed by alphanumeric characters, looking something like C03ABC1DA. When you apply this constraint with your own customer ID in the allowed values list, you prevent anyone from granting an IAM role to a Google account that belongs to a different organization. This is critical for preventing data exfiltration through IAM. Without this constraint, a malicious or compromised insider could grant a role like Cloud Storage Object Viewer to a personal gmail.com account or to an account at another company, and then exfiltrate data through that external identity. With the domain restriction in place, any attempt to add a member that is not in your customer ID list is rejected at the API level, regardless of how much IAM access the person making the change has. The first command shown discovers your customer ID. We run gcloud organizations list, which returns each organization along with its directory customer ID in the directory _customer_ ID column. You take that value and use it in the next command. The YAML file domain restriction. YAML declares the constraint in the constraint field, contains a list policy block, and within it an allowed values array with 2 entries. The first entry is your primary customer ID, which is the cloud identity tenant of your company. The second entry would be added only if your company has acquired another company that operates its own cloud identity tenant and you want to allow cross-organization access during the integration period. The gcloud resource manager org policies set policy command applies the YAML file at the organization node. The positional argument is the YAML file path. The organization flag specifies the organization ID as the target. After this policy is in force, any IAM grant to a principal outside your trusted customer IDs will be rejected, which closes one of the largest holes in default Google Cloud security posture. Creating a custom constraint. Let us walk through the concrete steps to create and apply a custom constraint. Our example will be a rule that requires every compute engine instance to have a label called cost center, which is a common requirement for accurate chargeback reporting. The custom constraint is defined in a YAML file called require cost center, YAML. The name field gives the constraint a unique name, and the format is organization/org_id/custom constraints/custom require cost center label. The custom prefix on the final segment is mandatory and signals that this is a user-defined constraint. The resource types field is a list specifying which resource types are subject to the rule, and we set it to compute.googleoffice.com/instance, which targets compute engine virtual machines. The method types field is a list specifying which API operations trigger the rule, and we set it to create and update so that both new instances and modifications to existing instances are checked. The condition field contains the cell expression that evaluates the resource, and we set it to resource.labels.costCenter exists, which returns true only when the instance has a label key named costCenter. The action type field is set to allow, meaning the policy permits the action when the condition is true and blocks it when the condition is false. The display name and description fields are human-readable metadata that appear in the Cloud Console. The first gcloud command is gcloud resource manager org policies set custom constraint, which registers the custom constraint with Google Cloud. The positional argument is the path to the YAML file containing the constraint definition. This step does not actually enforce the rule. It just creates the rule definition that can later be referenced by a policy. The second YAML file enforce cost center. YAML is the organization policy that activates the custom constraint. The name field references the constraint we just created using the format organization/org_id/policies/custom require cost center label. The spec block contains a rules array with one rule that has enforce set to true, which turns the constraint on. The third gcloud command is gcloud org policies set policy, which applies the policy. The positional argument is the path to the enforce cost center YAML file. The target node is specified inside the YAML file via the policy name, so we do not need a folder or organization flag on this command. After this policy is applied, any attempt to create or update a compute engine instance anywhere in the organization without a cost center label will be rejected at the API level. Managing the hierarchy and policies with Terraform. For real production deployments, you should manage the entire resource hierarchy and the organization policies as infrastructure as code, and Terraform is the most widely used tool for that purpose. The Google_folder resource creates a folder under a parent. The display_name attribute sets the human-readable folder name to production. The parent attribute specifies the parent in the format organization/org_id, which anchors the folder directly under the organization. The Google_project resource creates a project under a folder. The project_id attribute sets the immutable globally unique ID to webapp prod 001. The name attribute sets the display name. The folder_id attribute references the folder we just created, using interpolation syntax Google_folder.production.name, which Terraform resolves to the numeric folder ID. The billing_account attribute links the project to a billing account so it is funded from day one. The Google_org_policy_policy resource applies an organization policy. The name attribute specifies the target node and the constraint. In the format folders/folder_id/policies/constraint_name. We reference the production folder dynamically with Google_folder.production.name and target the compute.vm external IP access constraint. The spec block contains a rules block with deny_all set to true, which implements the deny all pattern for external IPs that we discussed earlier. The Google_org_policy_custom_constraint resource registers a custom constraint, with attributes that mirror the YAML structure we saw before. The name attribute uses the format organization/org_id/custom constraints/constraint_name. The resource_types, method_types, condition, and action_type attributes match the YAML fields with identical semantics. Managing the hierarchy and policies this way gives you 4 major benefits. The first benefit is version control, so every change is reviewable in a pull request before it lands. The second benefit is repeatability, so you can stamp out identical landing zones for different business units or acquisitions. The third benefit is drift detection, so Terraform will flag any manual changes made through the console that diverge from your declared state. The fourth benefit is integrated testing, so you can run policy validation tools like Terraform Validate and Connectist in your C pipeline before any change ever reaches Google Cloud. Design principles and best practices. To bring everything together, let us summarize the design principles that consistently produce well-governed Google Cloud environments. The first principle is to design the hierarchy before you create your first resource. Sketch out the folder structure that mirrors your business, decide on environment and department breakdowns, and document the policy decisions for each branch before any project is provisioned. Restructuring a hierarchy after workloads exist is painful and risky. The second principle is to apply broad guardrails at the highest possible node and exceptions at the lowest possible node. Set the baseline policies like external IP blocking, public bucket prevention, domain restriction, and service account key disabling at the organization node so every project inherits them. When a specific workload genuinely needs an exception, override the policy at the project level rather than weakening the parent policy. This keeps the blast radius of any exception as small as possible. The third principle is to lean on predefined constraints first and reach for custom constraints only when needed. Predefined constraints are maintained by Google, evolve with new services, and have been battle-tested by millions of customers. Custom constraints are powerful but they add maintenance overhead, so use them only when you have a requirement that no predefined constraint can express. The fourth principle is to manage everything as code using Terraform or another infrastructure as code tool. Manual changes through the console create drift, make audit difficult, and undo themselves the next time someone runs a pipeline. Every folder, project, IAM binding, and organization policy should live in version control. The fifth principle is to test your effective policy regularly. Use the gcloud Resource Manager org policies describe command and the new policy analyzer features to confirm that the rules you think are in force are actually in force after inheritance and overrides are resolved. Most policy bugs come from surprising inheritance interactions rather than from typos in the policy definitions themselves. Let me walk you through this final diagram. The well-governed landing zone is the goal, and it rests on 5 foundational principles. The hierarchy design principle establishes the structural backbone. The broad baseline policies principle applies guardrails at the organization root. The targeted exceptions principle handles workload-specific deviations at the project level. The predefined first custom second principle guides constraint selection. The infrastructure as code principle wraps everything in version control and automation. The 5 principles connect to and reinforce each other, and getting them right is the difference between a Google Cloud estate that scales smoothly and one that drowns in tickets and remediation. In the next segment, we will look at how to query and audit the policies that are actually in force using the Policy Analyzer, the Asset Inventory, and the Security Command Center, which is how you prove to auditors that your governance is working. Why audit effective policies? We have spent the first portion of our discussion designing the hierarchy and attaching organization policies. Now we need to address the other half of governance, which is proving that the policies you declared are actually in force and that no resource in your estate violates them. The gap between declared policy and effective policy is the single most common source of cloud security findings during an audit. A policy might exist at the organization root but be overridden at a lower folder. A constraint might be enabled in policy but have an exception list that is too permissive. A resource might have been created before a policy was applied, and now sits in a state that the current policy would block. Without a systematic way to query your environment, all of these conditions can persist for years. Google Cloud provides 4 interlocking services that together give you the ability to audit and prove your governance. The Policy Analyzer service answers questions about the policies themselves, like which folders have the external IP constraint applied and what the effective policy is on a specific project. The dry run mode for organization policies lets you stage a new policy and see what it would block without actually blocking anything, so you can test policy changes before they cause an outage. The Cloud Asset Inventory service holds a queryable database of every resource and every IAM binding in your organization, and lets you write rich queries to find non-compliant configurations. The Security Command Center service is the integrated dashboard that surfaces findings from all the underlying scanners and gives auditors a single pane of glass to review your security posture. Let me walk you through this diagram. The governance audit goal is the central concept, and it depends on 4 services. The Policy Analyzer service answers questions about declared and effective policies. The Dry Run Policies service simulates new policies before enforcement. The Cloud Asset Inventory service queries actual resource state across the organization. The Security Command Center service aggregates and prioritizes findings. All 4 feed into a single audit evidence outcome, which is the documented proof that governance is working that you present to internal auditors, external auditors, and regulators. Dry run policies for safe rollout. One of the most powerful but underused features of organization policies is dry run mode. Dry run mode lets you stage a policy that would normally block actions, but instead of blocking, it simply logs every action that would have been blocked. This lets you measure the impact of a new policy before you actually turn it on, which is essential when you are introducing a restriction in a large organization with hundreds of projects. A policy can have 2 specifications. The spec field is the live enforcement specification, and it is what actually decides whether actions are allowed or denied. The dry run spec field is the simulation specification, and it is evaluated against incoming actions but never blocks them, only generating audit log entries. You can have both fields populated at the same time, with the live spec doing nothing and the dry run spec testing what the new behavior would be. The YAML file dry run no external IPs. YAML shows this structure. The name field specifies the target node and the constraint, using the path organization/org_id/policies/compute.vm external IP access. The spec field is omitted because we are not enforcing anything yet. The dry run spec field contains a rules array with one rule that has deny all set to true. When this policy is applied, no actions are blocked, but every attempt to create or modify a VM with an external IP generates a cloud audit log entry with a dry run violation indicator. The first gcloud command is gcloud org policies set policy. The gcloud org policies set policy command applies the policy definition, and because the YAML contains only the dry run spec, the policy enters dry run mode. The positional argument is the YAML file path. The target is encoded inside the YAML file name. The second command queries cloud logging for the dry run violations. We use gcloud logging read to retrieve log entries from cloud audit logs. The query filter is the string protopayload.metadata.org policy violation info.policy type equals dry_run, which matches only entries that represent dry run violations. The limit flag is set to 100, which caps the number of returned entries to prevent overwhelming output during testing. The format flag is set to JSON so the entries can be piped into other tools for analysis. After running this for a few days, you will have a complete list of resources and identities that would have been blocked, and you can work with the affected teams to remediate before flipping the live spec on. Searching IAM policies. The single most valuable cloud asset inventory query type is search all IAM policies, because it answers the most common audit question, which is who has access to what. The first command demonstrates a basic search. We use gcloud asset search all IAM policies. The scope flag specifies the search route, and we pass organization/org_id to search the entire organization. The query flag specifies the filter expression, and we pass the string policy, role, permissions, resource manager, projects, delete, which matches any IAM binding whose role includes the resource manager.projects.delete permission. This returns every identity in the organization who could delete a project, which is exactly the kind of high privilege query auditors care about. The output includes the resource being protected, the role bound, and the member identities. The second command searches for IAM bindings to a specific user. We invoke gcloud asset search all IAM policies again. The scope flag is the same organization level search route. The query flag this time is the string policy, user:admin@example.com, where the colon syntax matches any binding that mentions that user as a member. This returns every place in the entire organization where this specific user has been granted any role, which is the answer to, what does this person have access to? When an employee leaves the company or an account is suspected of compromise, this is the query that produces the cleanup task list. The third command searches for bindings to external identities. The scope flag is the organization. The query flag is the string policy, gmail.com, which matches any binding that grants access to any gmail.com address. In a well-governed environment with the domain restriction constraint in force, this query should return 0 results, but it is your verification step to confirm that no historical Gmail bindings have leaked through. The fourth command outputs results in JSON format. We add the format flag set to JSON to the previous query, which makes the response machine parsable. This is essential when you want to feed the results into a remediation pipeline, a compliance dashboard, or a script that produces tickets for the security team. Exporting asset inventory to BigQuery. For ongoing analysis and trend detection, the right pattern is to export cloud asset inventory to BigQuery on a schedule, then query the data with SQL. BigQuery makes it trivial to compare today's state to last week's state, to count violations over time, and to join inventory data against billing data and audit log data for unified analysis. The first command provisions the destination dataset. We use BQMK to create a BigQuery dataset. The dataset flag is set to true to indicate this is a dataset operation. The location flag is set to US, which keeps the data in US multi-region storage. The positional argument is the dataset path, which is the format project_ID:dataset_name. So security audit 001:asset_inventory creates the asset_inventory dataset in the security audit 001 project. The second command exports the asset inventory. We use gcloud asset export. The content type flag specifies what to export, and we use resource to export resource assets. To export IAM policy assets, you would set this flag to IAM policy, and you can run the command twice with each value to get a complete picture. The BigQuery table flag specifies the destination in the format project/project_ID/dataset/dataset_name/table/table_name. We export to a table called all_resources_snapshot. The organization flag specifies the scope to export, and we pass the organization ID. The output BigQuery force flag is set to overwrite the table if it already exists, which simplifies recurring exports. After the command completes, BigQuery contains a complete snapshot of every resource in your organization with their metadata. The third command is a BigQuery SQL query that finds external IP violations using the exported data. The BQ_query command runs a query against BigQuery. The use_legacy_SQL flag is set to false to use standard SQL syntax. The query selects the name field and the location field from the all_resources_snapshot table, where the asset_type field equals compute.googleoffice.com/instance, restricting to compute engine VMs, and where the additional underscore attributes JSON contains access configs, indicating an external IP. The result is the same list of public VMs we could get from the search all resources command, but now persisted in a queryable warehouse where we can compare snapshots over time and produce historical trend charts. You can schedule this export to run nightly using Cloud Scheduler and Cloud Functions, and you can build Looker Studio dashboards directly on top of the resulting tables for executive-level governance reporting. Remediation workflows. Detection without remediation is half a solution. Once you have audit evidence showing non-compliant resources, you need a structured workflow to fix them. Google Cloud supports 3 main remediation patterns, and most mature organizations use a combination of all 3. The first pattern is manual remediation through ticketing. A finding is generated, a ticket is opened in Jira or ServiceNow, an engineer reviews the finding, makes the change through Terraform or the console, and closes the ticket. This is the slowest but safest pattern, and it is appropriate for high-stakes resources where automated changes could cause an outage. Most enterprises start here for production workloads. The second pattern is gated automated remediation. Findings are routed to a cloud function or cloud run service that knows how to fix common categories of violations. The function does not execute the fix directly, but instead opens a pull request against your Terraform repository proposing the change. A human reviews the pull request and approves the merge, after which the standard C pipeline applies the fix. This pattern combines the speed of automation with the safety of human review. The third pattern is full automated remediation. Findings trigger a cloud function via pub/sub that immediately fixes the violation. For example, a finding that a bucket has been made public triggers a function that strips the all users binding within seconds. This pattern is appropriate only for clear-cut violations where the fix is unambiguous and the cost of action is low, like removing dangerous public IAM bindings. The code block shows the gcloud commands to set up a pub/sub notification feed from Cloud Asset Inventory. The first command is gcloud asset feeds create. The positional argument is the feed name, security feed. The organization flag specifies the scope, the organization ID. The asset types flag is set to compute.googleoffice.com/instance to monitor only compute engine instances, but you can list multiple types. The content type flag is set to resource to receive resource state. The pub/sub topic flag specifies the destination, in the format project/project_ID/topics/topic_name, and we use project/security audit001/topics/asset changes. After the feed is created, every change to any VM in the organization is published to that pub/sub topic in real time. A cloud function subscribed to the topic can then evaluate the change and trigger the appropriate remediation pattern. Bringing it all together. We have covered a lot of ground, so let me close with a summary of the complete governance lifecycle and how all the pieces fit together. The lifecycle starts with hierarchy design, where you sketch the folder structure that mirrors your business and decide where each environment, department, and team will live. The hierarchy is the foundation that everything else inherits from. From hierarchy design, you move into policy definition, where you select the predefined and custom organization policies that encode your guardrails, and you express them as Terraform code in version control. Common starting points include external IP restriction, public bucket prevention, domain restriction, and service account hardening. From policy definition, you move into safe rollout, where you deploy new policies in dry run mode first, collect the audit log violations for a few days, work with affected teams to remediate, and only then flip the live spec on. This avoids the disaster of breaking dozens of teams with a single overnight policy change. From safe rollout, you move into continuous audit, where Cloud Asset Inventory feeds into BigQuery on a nightly schedule. Security Command Center continuously scans for violations, and Policy Analyzer commands answer ad hoc audit questions. The audit feeds findings into your dashboards and ticketing systems. From continuous audit, you move into remediation, where findings are routed through manual, gated, or automated patterns depending on the severity and the resource type. Remediation closes the loop and brings the environment back into compliance. Let me walk you through this final diagram. The governance lifecycle is the central concept, and it consists of 5 stages connected in a continuous cycle. The hierarchy design stage flows into the policy definition stage, which flows into the safe rollout stage, which flows into the continuous audit stage, which flows into the remediation stage, which loops back to hierarchy design as the cycle restarts whenever the business changes shape or new requirements emerge. Each stage uses the specific Google Cloud services we have covered, with Resource Manager and Terraform handling hierarchy design and policy definition, with Dry Run Policies handling safe rollout, with Cloud Asset Inventory and Security Command Center handling continuous audit, and with PubSub and Cloud Functions handling remediation. Mastering this lifecycle is what separates Google Cloud estates that scale safely from those that collapse under their own complexity. That covers the complete picture of building and governing a GCP resource hierarchy with organization policies, from the first folder you create to the audit evidence you present to regulators. Thank you for your attendance. Please consider subscribing to the channel and liking this video.